Have you ever noticed when an ambulance or an ice cream truck is moving towards you that it sounds high-pitched? It sounds different when it's moving towards you, but once it moves past you, that it starts to sound terrible. Have you guys noticed that before? Let me show you what I mean. I have a recording here of an ambulance. Let's take a listen. Okay, so I have no doubt that we have all heard the sound of an ambulance before. That is not what I was showing you. What I wanted you guys to hear from this video that I just played was that the sound the ambulance was making as it was moving had a different tone to it. So I'm going to play it again, and I want you guys to listen, and I'm going to do this too. I want you guys to listen and see if you can pick up the sound differences as the ambulance is moving towards me and when it's moving away from me. So I'm going to do it again, and I'm not going to look, and let's see if I can figure it out. So the ambulance is moving towards me, it's moving towards me, and then it's going to cross, and then it's going to start moving away. Did you guys catch the difference in that tone? Changes in that tone is because of the frequency of sound waves. They are increasing as that ambulance was moving towards me, and then decreasing as that ambulance was moving away from me. These changes in pitch, which occurs for both sound and light, these changes in pitch, that concept of that sound change, that concept is known as the Doppler Effect, which again refers to the perceived change in frequency of a wave that is emitted from a source. So a wave that is coming from somewhere. So in this case, the sound wave, was coming from the ambulance. So let me say that again. The Doppler effect is the perceived change in frequency of a wave that is emitted from a source that is either moving towards an object or away from an object. So in this example, the ambulance was the source of a wave, and it sounded high-pitched as it was moving towards me, and it had a lower pitch as it was moving away. Now, as frequency and wavelength are an inverse relationship. Well, what does that mean? What that means is, as frequency decreases, wavelength increases. So the waves are getting longer. And the opposite is also true. As frequency increases, wavelength decreases, so they get shorter. So one more time in this example, as frequency increases, the wavelength is getting shorter. So the frequency is increasing as it's getting towards me, increasing. Then once we get on the same plane, as it starts moving away, that frequency starts decreasing. That wavelength starts getting longer. Let me draw that out. I'm going to draw that out for you as another example. So we heard the example. Now let me draw it out for you for a better explanation. So let's continue from the sound that we just listened to. So here's my stick figure, and here is my very sad car. I can't draw very well. Here's a car with the siren, and it is moving towards me. It's moving in this direction. The sound that it is making, the wavelength is going to appear shorter and shorter, and then as it starts moving away from me, the wavelength is going to become longer. When we start talking about waves or wavelength, let me switch colors. Wavelength. Okay. Wavelength is the measurement between 2 points of a wave. It doesn't matter if it comes from the top part, but the top of a wave is not called the top of a wave. The top of a wave is called a crest. And the bottom of a wave is called a trough. It's called a trough, not like Toph from Avatar series. No, it's called a trough. There's an R in there. The crest is the top of a wave, and the trough is the bottom of the wave. And the wavelength is the distance or the measurement between those 2 points. Now, as we start moving further and further away, that distance is getting longer, whereas on this side, the way I drew it anyway, it is significantly shorter. That is our characteristic of our sound wave. Well, the same holds true for a light wave. In our electromagnetic spectrum, all of these emit some sort of light. We just can't see them. We can see the visible light. And the light also has that same wavelength characteristic, where between those 2 points is your wavelength. Red light has a longer wavelength, where blue and purple have a shorter wavelength in the sense of light. Same thing for sound. If it is moving towards you, the wavelength is shorter. The wavelength is decreasing, and as it's moving away from you, the wavelength is increasing. It's getting longer. Now, with the concept of light, let's look at the light concept. Okay, so here is Earth and here is a star. Now, do you recall of the 3 types of spectrum, continuous, absorption, or emission, looking at this diagram, which one is this? If you said absorption spectrum, then you are correct. We know that this is an absorption spectrum because it appears to be continuous, yet there is a black line or a dark line on the spectrum. It's probably not the best, can't really see it, but there is one here and there is one here. So let's talk about that shift, moving towards and moving away. Well, in this example, and we have our wavelength, in this example, we'll go from here to here. This star is in line with Earth, okay? In this example, example A, the star, it's got an arrow, so it is moving towards Earth. Well, if this is our original star's point, and if this is saying this is what it should look like if it's stationary, if it's parallel, if they're in the same line. If the star is moving towards us, there's going to be an apparent shift in the spectrum. And we know that, and I'm going to switch colors here, because the original point was between the yellow and the orange color. So the original point was here, yet it has shifted over towards the blue side. So this would be a blue shift, which means it is moving towards Earth. And the opposite holds true on this side. In our sound example, if it is moving away from us, the wavelength is getting longer, right? The wavelength is increasing. Same thing here. The wavelength is increasing. And if we look, if the original point in our original line was in the center, on this side, our star is moving away, it is going to shift towards the red. It is going to move away from us. We call this a red shift. So it's moving away from Earth. And that is your light example of the Doppler effect. Sound example of the Doppler effect. If the sound of the source of the sound is moving towards you, the observer, the wavelength is going to be shorter. It's going to be decreasing wavelength if it is moving towards you. If it is moving away from you, wavelength is increasing. That is for sound. Same thing for light. If it is moving towards you, wavelength is getting shorter. We call that a blue shift. It's moving towards Earth. So we can look at the wavelength and we can compare the spectra of the moving star towards the stationary star, and we can see between these 2 points, it has moved to the right. Right movement towards the blue color, blue shift. And if it is moving away from us, wavelength is getting longer. So it is increasing. And it appears to have left movement. We call that red shift. It is moving away from Earth. And that is your Doppler effect explanation.